guys, this is another video. So we'll be looking on a concept of a certain concept in calculus 2. We say the area of surface of revolutions. So we have two. So it's just further integration. Okay. So like my next video, I will talk of volumes of surface of revolutions. So in areas of surface of revolutions, we have, I'll just start with just a rough knowledge on that. So the knowledge is derived from the concept of a frustrum. So we usually say the area of a frustrum, area of a frustrum equals to 2 pi RL. Okay, so there's a way the formula that we'll be writing will be derived, but for this case, this video will just look on how to handle questions on area of surfaces of revolutions. So in areas of surface revolutions, let me just explain more. So we'll look on this formula, how to apply this formula to calculate areas of surfaces of revolutions. So just an example, we usually have two graphs where in areas of surface of revolution we are trying to rotate the curve given by any integral or any function. We usually rotate the curve along either the x-axis or the y-axis. The x-axis is just the same as the horizontal axis. The y-axis is the vertical axis. So I'll just draw the two graphs to show the rotation. So for example, I rotate my curve. So we have this graph, okay? So this is the y-axis. So this is the x-axis. So if I told I'm rotating the curve, okay, let me say the curve is this. For example, this is the curve. Okay. Let me say y equals to x squared, for example. So this is the curve I'm told to rotate. So I'm rotating this curve along the x-axis. Okay. So I'll be rotating the curve along the x-axis. So I'll get my replica. The replica for this is just same as reflection. So I'll just reflect this curve to this other side, the opposite of the x-axis. So I'll just get something like that. For example, something like that. So these are rotated. So the areas of surface I've rotated this curve along the x-axis. I'll get something like that, for example. So this is my rotation. Okay. Let me clear that. So when you rotate this line or this curve about the x-axis, the supposed diagram is this. Okay. Again, let's rotate the same curve along the y-axis. Okay. So I'll have this graph. I'm rotating the same curve along now the y or the vertical axis. This is along the x-axis or the horizontal axis. Okay. So let me rotate the same curve, y is equals to x squared, along the y-axis. Let me say this is my x, this is my y. So let me rotate so the curve will look like just the same. So assume this is the curve. So if I rotate it, it will just give me the same reflection, but on the other opposite side. So I'll get something like that. And the curve is y equals to x squared, for example. Okay? So So, as I was saying, we are rotating the curve. This is the curve along the y-axis. Okay? So we just get the same replication. So just with something like that, for example, something like that. So we have rotated that along the y-axis. So how will we calculate the area of this surface, the area of this surface, and again the area of this surface? So we have two formulas on that. So this along the x-axis, okay? Along the x-axis, we have a different formula. So again, this other side, this is along the y-axis or the vertical axis. So we have two different formulas for that. Okay, the formula is just the same. So from here, I will say, let's compute from here. I will say my area for the x-axis, my area, okay, equals to 2 pi. I will write, so like, okay, we'll just be integrating. The area there will be the integral, okay? This is calculus 2, so we have to deal with integration. So the curve will be integrated from this point, let me say from A, okay, to B, from A to B. So the curve again here from A to B. So as you can see, so it will be, the area will be now the integral, okay, from A to B, right? 2 pi, as you said, 2 pi, okay, multiplied by the radius, okay. But now let me explain this radius. So if you are dealing with the x-axis, okay. So from here, let me explain from here. So if you are dealing with the x-axis, someone can, let me write in a different pen to show you the radius, how it's being approached. So from here, assume this is a cone, okay? This is a cone. So the radius, for example, is from here, the center, up to the curve, okay? Up to the curve. So this is the radius r. So as you can see, this is just the value of the y-axis, okay? It's just the value of the y-axis. This is the value of the y-axis. So I'll just read my y-axis. Just read my y-axis. So that will be the radius. So this will be the, so I'll just read my y-axis. So it's from here. So my radius is that. So this is my radius. So in here, so I'll write the radius as a function of y. So I'll write f of x. So the radius is the y value, okay? But I'll write it as a function of x. So I'll write my radius as a function of x. So it will be r of x, okay? R of x, so it will mean, okay, I can say y of x, but dealing with r, I'll just say r of x, okay? It's just a function for that. So I'll write as r as a function of x. That will be my radius. So in short, I'm trying to say the radius along the x-axis, when you're rotating along the x-axis, is just the y value. It's just the y, okay, it's just the function of curve. For this case, for example, my r here will just be x squared, okay? The y value is just the radius along the x-axis. Along the x-axis, the radius is just the function, or just the curve. Y is equals to, so it's just the value of x, or the value of y, sorry. So, for example, according to this case, I'll just use x squared. Then, from here, what's my length? Okay, we have dealt with pi r, 2 pi. We have dealt with r. We are now looking at length. So this is the arc length. L, okay, let me write L represents the arc length. Okay, so arc length. I've created a video dealing with how to approach questions on arc length. So check on that video. We'll get our arc length L using the formula the square root of 1 plus, okay, the first derivative of f of x, then we square it, okay, dx. This is my arc length. Sorry, let me put an integral sign here. There's an integration sign from A to B, so that's my arc length. So my formula we said, from this formula we calculated our arc length. My video will show how we came up with the arc length formula, my next video. So I'll just replace my arc length with this formula. But now, before I do that, let me explain. Okay, when you are dealing with the x-axis, given a function like y is equals to x squared, we usually find, I'll just replace it here. Okay, look here, my first derivative as dy dx is just the same. So I'll just clear here. Instead of f of x prime, I'll just write my dy dx. Okay, so I'll get my dy dx. So in here, according basing on the x-axis, I'll write dy dx. Take note here because the formula will differ. For the y-axis, here will change. It will be the opposite. Okay, so I'll get my dy dx squared. While I'm rotating on the x-axis, I'll get my dy dx. It's just the same as f prime of x. Okay, so having this, I'll just replace this formula to this L. Okay, so here I'll multiply it by L. But what is my L? My L is the integral. My L is the integral. Okay, not the integral, the square or the rad. Okay, the rad of 1 plus dy dx, okay, squared. Okay, then I'll place my, we are rotating along the x-axis, so it will be dx. Okay, so this is my formula for calculating area of surfaces of revolution along the x-axis. Okay, so this is my area. This is the area of surface of revolution. If I'm told to rotate the curve along the x-axis, I'll use this is the formula I'll use to calculate the area of surface of revolution, right? So having this knowledge, I've already cleared that. So let's operate along the y-axis. Along the y-axis is where now I'm rotating this curve along the y-axis. So the graph looks like that. So I'm rotating along the y-axis. So the formula looks the same. Okay? So the formula for the revolution along the y-axis, this is along the x-axis. Let me just write. So this is along the x-axis. Okay? The formula along the y-axis is just the same, but the difference will come from here. So my formula again, along the y-axis, okay, will be area equals to the integral, just the same, right? The same things, a to b of 2 pi multiplied by, so from here, my r, let me consider my r. So from here, let's find our r. So the r, the radius is, for example, from here to here. Okay, this is my radius. That's my radius. It's just the same as me finding my x value. So this will be my radius. So my radius for the y-axis is just the value of x, not a function of x. In x-axis, I said my radius is just a function of x, which is just the same as the graph itself, the function, the value of y. But now, in the y-axis, my radius will be just the value of x-axis, okay? My radius will be that value of x-axis. So I'll just write my radius, not the differences, the formula. So it's just the value of x-axis, not a function of x, okay? Multiplied by, here again, just have the same thing, okay? 1 plus, but now, in the dy dx, it's now the opposite, it will be dx dy, okay? So it will be dx divided by d of y. Then I square that, okay? Now we are rotating along the x-axis, the y-axis, so I'll get my dy. So these are the two formulas when computing areas of surfaces of revolution. So from here, with this knowledge, let's look at an example. Let's look at an example for us to familiarize. So guys, having that knowledge, so this is an example. So we try to evaluate this example using the knowledge we have said. So the example says the curve y equals to x, y is equals to the rad of 4 minus x squared. The interval is from -1 to 1, is an arc of the circle that, okay, find the area of surface obtained by rotating the arc about the x-axis. So let me just try to explain what these statements mean. So this is just a circle. So for example, just we have something like that, for example. So the circle maybe, that is the circle. I'm trying to just explain. Okay? I'm trying to explain. This is the y-axis, this is the x-axis. So this is the circle with this graph. This is usually r squared. Okay? So r squared is the same as 4. So my r is just 2. Okay? So the area of a circle, as you know, so the area of that circle, the radius will be r squared. So that will be 2. So from here to here it's 2. Okay? But now there's an arc. So there's an arc of this circle. So we have removed all the parts of the circle. We have remained with an arc. So the arc is just y squared equals to 4 minus x squared. So let's say it's being rotated along the x-axis, for example. So let me just clear from here, maybe. Let me clear from here. Let me clear from there to here. Let me clear this. I'm trying to show the curve. Okay? I'm trying to show the curve. So the circle was that way, so I'll just have something like this. For example, so let me say this is the curve. So let me say this is the curve. Okay, so this is the arc. The arc. What is an arc of a circle? An arc is just a portion of the circumference. Okay? So the arc, so this is the curve. The circle is that hole, that's an ellipse. Then an arc is just a portion of that circumference. So the portion of that circumference is represented by y equals to the square root. Okay, equals to the square root of 4 minus x squared. Okay, so that's my, I'm trying to explain that. Okay, so we have something like that. So we are trying to rotate this curve along the x-axis. We are trying to rotate that curve along the x-axis. Along the x-axis. So we'll get just a reflection of the curve on the other side, so something like that. Just get a similar reflection. Okay. So let me place some. So the diagram looks like that. So this is the diagram. Okay. We've just done a reflection of the curve. So I've tried to draw that. So this is what we have. So when finding the area of this, we said the formula is, what was our formula? Let me write the formula. We said along the x-axis, we said the area, along the x-axis, we said the area equals to the integral from a to b 2 pi, okay, multiplied by, we said what's our radius? Our radius is function of r, so it will be function of x, okay, which is just the same as the y value, okay, multiplied by the square root, of 1 plus dy dx, remember? Dy dx, not dx dy. Dx dy is for y-axis, multiplied by, so we are rotating along the x-axis, so automatically it will be our dx. Okay, so this is our formula, as we say. So just let us replace the values, so we get equals to the integral of, the interval is from -1 to 1. So okay, so from -1 that's the lower side, so it's just -1 to 1, okay, 2 pi multiplied by, what's our r squared? Our r squared is just the function of the graph, which is just the function of just the y-axis, the y value, okay? So for this case, the y value is that, so it will be the square root of 4 minus x squared, okay? Multiplied by again the square root of 1 plus the dy dx. Okay, so let's find our dy dx. What's our dy dx? So let's find our dy dx. So from here, I'll write my y is, equals to the square root of 4 minus x squared. Something like that. So I will say my dy, okay, let me just do some further simplification. I'll take my root. This root is just the same as raised to a half, okay? So I'll just 4x minus 2 raised to a half, okay? So there I'll do my differentiation. So I'll differentiate y with respect to x. So I'll get my dy dx to be, okay, from here, this is general power rule. I'll take my a half in front, I'll get my a half multiplied by the function itself, 4 minus x squared, we usually say minus 1. So it will be a half minus 1 is just negative a half, okay? But again, don't forget to multiply by the derivative of the inside, because this is just chain rule. This is chain rule, so the derivative of the inside will be negative 2x. Don't forget that. So from there, I'll get my dy dx. So my 2 will go with the 2 there. Okay? So to my supposed answer, I'll write negative of x, I'm remaining with negative of x. Okay? So this negative, okay? this negative will make my square root to go below, so I'll get over, then a half is just the same as 12, so I'll just write the square root of this. Square root of 4 minus x squared, right? So from there, I want removing the rad. Okay, usually say perform SATs. Usually perform SATs, okay? But for this case, just square this. If you square this, it means you'll have to square this. Just remain the same. If you do, if you perform anything here, just perform again on the lower side. So if I square my value, I'll have to square my denominator. So I'll get x squared is just the same as x squared divided by, if I square this, I just remain with 4 minus x squared, right? So that is just my dy dx. Okay? So my dy dx I'll get as that. So I'll write x squared, divided by 4 minus x squared. Don't forget to place, sorry, we didn't square, so don't forget to square it, okay? Then don't forget to write d of x. So from here, let's, okay, from there, so, okay, so sorry guys, I performed a square here, my dy dx, so if I square this, I just have again to square this other side, so I'll get my dy squared. So this is my second derivative, which that's wrong, I just want my first derivative, so sorry, I won't square this, we just have to clear that, it's not necessary, because if I square this, I'll have to square again this side, so it will be my d second y dx second, that's my second derivative, so I won't do that. I want my first derivative alone, okay? I want my first derivative alone. So my first derivative alone will be that. Okay, I did a wrong. So I'll just get my negative. Okay, just clear that. And again, I'll just place my rad. Okay, sorry, I'll just place my rad there. Remember, my rad is just there. So again, I'll just replace here. Let me replace here with what I've gotten. My answer is that. So I'll just replace with negative x divided by the square root of 4 minus x squared. Then all this thing, I square it. Okay? So let's do further simplifications of this. Okay? So for this, I will write, if we square this, I'll just square x squared, I'll get x squared. Then if I square this, the rad goes out, I'll get 4 minus x squared. So if I square this thing, I'll get this. So I'll just clear this thing and put that. Okay, allow me to do that. Negative of x multiplied by negative of x is just x squared, so it will be x squared divided by 4 minus x squared, right? So from there, I will make, again, performing here again, we just have to do our computations from here. Again, performing here, I will make this to be with a common denominator. So performing my LCM, I will get 1 over 1 plus x squared over 4 minus x squared equals to, okay, the normal LCM, my LCM is 4 minus x squared. So I'll just multiply by the 4 here, multiply the 4 here, so I'll get my 4 minus x squared plus x squared. Okay? So that will be my answer. So my x squared goes with x squared. I'll remain with 4 divided by 4 minus x squared. So all the expression inside the rad, I'll replace with that. Okay, so let me clear this. That was just a simple explanation. So all these I'll replace with that. So I'll clear this. I'm going to be doing the computations with that. So it will be 4, okay, divided by 4 minus x squared, okay, minus x squared. Okay, so from here, let me write something. The square root of 4 divided by 4 minus x squared is just the same as if I find the square root of 4 divided by the square root of this. So I'll just clear this and separate the square root to each term. So from there, we have said this is our expression from there. Let me clear this. So sorry, I'll just split the integral that. Splitting that, I'll just get 4 to its own square root. This again to its own square root. So I'll get the area as the integral from -1 to 1, 2 pi, okay, multiplied by the square root of 4 minus x squared multiplied by the square root of 4, okay, divided again by the square root of 4 minus x squared. Don't forget placing d of x. As you can see from here, it's easy. This goes with this, so this cancels this, okay? Life is easy. So we'll remain, okay? We'll remain with the integral from -1 to 1 of 2 pi, okay? I will explain that. 2 pi multiplied by, what's our square root of 4? It's just 2. Okay? Square root of 2. D of x. But remember, 2 pi, I could have first get it outside the integral. So 2 pi is just a constant, so I'll get it outside the integral, but we won't take 2 outside the integral. Okay? We'll have to remain with 2 for us to integrate 2. Okay? So I'll clear here. I'll clear all. Okay, so I'll remain with the integral of, so I'll take my 2 pi outside, it's a constant, so I'll take my 2 pi outside from -1 to 1, 2 d of x. Okay? So I'm integrating 2 with respect to x. Okay? So my answer is just 2 pi, okay? This 2 pi multiplied into 2 with respect to x, I just add an x, a variable to that, so I'll just get 2x, right? I just get 2x. Then I'll replace my bounds from -1 to 1. Okay? So what will be my answer? So I'll get 2 pi. I replace 1 to the x, I'll get 2, okay? This will multiply all that to be multiplied by 1, okay? Minus